And in the end, we actually going to have this. We're actually going to have that. Okay. Now, if you have that, what you have now is what we call posterior. And when you take a look at that posterior, please, I need you to pay attention. Inside the square root, apart from the 2 pi, what do we normally have? Sigma square, right? Variance. Inside the square root, apart from the 2 pi, the other one is the variance. Then it means here that is the variance. Do you see that? That is the variance. Now, what about mean? Of course, mean is something here, right? Then this guy, that is why this is the mean. Because it is the mean, that is the variance. But let me tell you this. Don't care about this. I'm actually going to put it in a simplified way. And you're going to see what is coming in the exam. Now, pay attention. I've already simplified this. Are you ready? Okay, let's take a look at this. If I want to talk about normal, this is for application now. This is what I'm bringing. I will leave the other derivation to those who want to come for higher level statistics, masters or PhD. Okay, now I want to give you a computational example. Normal prior with normal posterior. Okay, a normal prior is going to be a conjugate prior to normal likelihood because the posterior density will be normal. Now, you need to first start with a prior belief. From there, we collect our data to update our belief. This is our data. Does that make sense? Now, based on our data, we're going to have a likelihood distribution. Please follow. Please, I need you to pay attention. The likelihood distribution is going to be this. In my likelihood distribution, the theta is the mean. We don't know it. But the variance is known. Does that make sense? We know the variance. Okay. We don't, of course, I don't we know the variance, but we don't know the mean price. Now, and our theta that is unknown, the mean, is a parameter, is a random variable. Does that make sense? Now, we need to have a prior knowledge before seeing this data. Then we're going to create a distribution for the prior. The distribution for the prior, I need you to pay attention, is going to be this. Whenever I'm writing a prior distribution, the parameter will be random variable. The parameter here is theta. Now, you can see mu prior, that is a prior mu. It means the theta, before seeing the data, the theta followed normal distribution with the mean and the variance. You can see in this one now, that's a normal prior. You're actually going to know, you have the knowledge of the mean, you have the knowledge of the variance, but in the likelihood, you only have the knowledge of the variance. You don't have the knowledge of the parameter. Does that make sense to you now? Okay, now how will the posterior look like? Posterior is also going to be normal. Okay, posterior will be normal, and we're still going to have parameter theta follow normal. We're going to have a posterior mean. We're going to have a posterior variance, but how are we going to get the posterior mean and the posterior variance? The posterior mean is going to be a function of the prior mean and likelihood mean you're going to see. Any question up to this point? Any question? Go ahead. Yeah. Okay. Okay, should I repeat what? We don't know theta. We don't know the mean. I will show you. I will show you that. Okay, you know, the most important is getting the this and that, right? The posterior mean and the posterior variance, right? Okay, before showing you, I first want to show you something. How is a prior is going to look like? Take a look at this. Can you see that? Like I said, a prior follow normal, okay? And we know the mean, you know, in a prior belief, we know the two. Okay, we know the two parameter. We know the mean, we know the variance. This is the way distribution is going to look like. C1 here is that 1 over, that's a constant, that's a normalizing constant. Okay, any question about the structure? This table is very important. Now, let's go to the likelihood. The likelihood is when we have data now. Please pay attention. When we have data, we don't know the mean, but we know the variance. Go ahead. Because we have an assumption in statistics that we have some, you know, when we're doing hypothesis testing the other time, I said when the population variance is given, and when the population variance is not given, when the population variance is given, we normally use z-test. When the population variance is not given and the sample size is small, we use a t-test. Moving forward in statistics, we got a lot of assumptions. Does that make sense to you now? Now, that is a likelihood. Now, let's now go into the posterior now. Okay? Let's now go into the posterior now. Oh my God. Look at the posterior now. We don't know any of them. We don't know the posterior mean. We don't know the posterior variance. And you can see C1, C2, C3, all of them is going to have stuff like this. That's just a normalizing factor. Okay, does that make sense? Now the question is, how am I going to get the posterior mean and the posterior variance, right? Now, take a look at this. Oh my God. You need to write this guy down. You need to write it down for the purpose of this exam. The posterior mean is A multiplied by the prior mean. You already know the prior mean. How am I going to get A? What is A? A is 1 over posterior variance. Sorry, 1 over prior variance. Does that make sense? And B is the number of your data divided by the sigma squared. Where is the sigma squared coming from? That is the likelihood variance. Okay, then you can see that now. Then look at the posterior variance. Posterior variance is 1 over A plus B. This is very important. Does that make sense to you now? You need to write this down. This is a formula. Because the probability that I'm actually going to set this in the final is 1. Okay? You need to write this down. Can we go into the example right now? Okay, let's go into the example now. Suppose we have one data. What does that mean? N equal to 1. Does that make sense? Suppose we have one data point, S equal to 2. That's a one data point. Draw from, pay attention. Draw from, what is that? Theta and 3 square, what is that? Likelihood. That is a likelihood. I told you in the likelihood, we don't know theta. We know the likelihood variance, but we don't know the likelihood mean. Okay, you should be able to know how to identify them. Suppose theta is our parameter of interest with, what is this? Oh my God, the two are given. That's a prior distribution. Does that make sense? You have the prior now. You have the likelihood. You can now look at the question. Let's go to the question. Oh, my question is going to look like this. My question is going to look like this. Let's take a look at number 1. I'm actually going to ask you to identify what is your prior mean. What is your prior standard deviation? Of course, when you know the prior variance, you find the square root of that. What is sigma? The sigma here is different from this one. This one is the one from where? From the likelihood. You see 3 square, right? Okay, then what is your n and what is your x bar? Okay, the next question say make a Bayesian update table. I'm going to show you the table now. but leave the posterior as an unsimplified product. Then the next one, use the updated formula to find the posterior. Let me show you the table now. Oh my God, I'm going to ask for the table. If you want to curate the table, you're going to write prior. You write the distribution given. Can you see that? You've been given that. Likelihood, you write the distribution given. Posterior, you write the distribution given. And this is going to be the corresponding normal density for each of that. Is there any question who doesn't know how I actually set up this table? Is there anyone? What am I going to do now? I'm finding my A, finding my B, finding A plus B, find the posterior mean, find the posterior variance. Look at that. You know, what is the formula? That's why here, this is very important. Can you see that? Very, very important. Do you know that the moment you have A and B, the moment you have A and B, you can get a posterior variance. Okay, in the end, that was what we got here. Take a look at this. At the end, you know, I said this is my posterior mean. Give me 1 second. I'm going to clean up so that you can see it very well. This is my posterior mean, and this is my posterior variance. If I have my posterior mean and my posterior variance, how am I going to write the posterior distribution? I'm actually going to write it this way. Look at that. I'm going to say f of s given x, you know, is one data point. Given s equal to 2, we follow normal with the posterior mean that you got and the posterior variance, period. Just get your 100%. Is that not super easy, right? Is there any question? Is there any question? I want to put something as an exercise. You can just take a look at this. On a basketball team, the players are drawn from a pool in which the career average free throw percentage follows that. Can somebody tell me? What is this? Is this posterior distribution? Is it likelihood? Is it prior? Which one? Everyone. Prior, because the two are giving. Good job. You're doing great. That's a prior, right? Okay. In a given year, individual player free throw percentage is this. What is that? Likelihood. Good job. You guys are doing great. Where theta is their career average. This season, Sovili made 85%. 85% of a free throw. What is the posterior expected value of a, here they are asking you only posterior mean. You have all the information that you're actually going to use to figure it out. Does that make sense to you now? Go ahead. Yeah, whenever, you know, that is the idea of Bayesian inference. Getting posterior is combining prior information with the likelihood. We're always going to do that. Does that make sense? Watch out. Okay. Now, but prepare, you know, what is very important is this guy. That's what is important. As far as normal prior, normal likelihood, and normal posterior is concerned, the moment you understand that, super cool. And don't forget the table. Well, if I ask you to generate, look at that. Look at, I think I said that here. I said that here. Make a Bayesian update table. When I say make a Bayesian update table, that is what I mean. You know, this is the table. Okay. Now I want to move right now. I'm leaving this as for Monday. This is the solution. This is going to be part of the practice question. Okay. So I'm leaving that one for Monday. Now, I'm going to do this in the last 10 minutes. But this is not going to be part of the final. Does that make sense? What we want to do now is not going to be part of the final. Talking about Bayesian credible interval, you just need to, we just wanted to, because when we're using frequencies approach, we have a way to construct confidence interval, right? And when we're dealing with a Bayes estimator, we're also going to have a way. So we call that Bayesian credible interval. Okay. Now, I said the parameter, don't forget the parameter theta is a random variable under Bayesian setting. And what distribution we normally use? Posterior. Does that make sense? We believe we've combined our prior belief with the likelihood. Let's say that is a G of theta. Okay, if we consider an interval A and B, the posterior probability random variable is going to be that we see here. Just like the probability of a theta line between A and B. And we can disclose level of confidence, level of confidence like 90%, but in the Bayesian framework, we normally call it 90% credible interval. Credible interval. Okay. Now you're given all of these. Okay. They give you all of this. And the question, and it's normal. Of course, this is application of a normal that I talk about. The question says find the 95% within 2 standard deviation. We also, in a Bayesian setting, apart, the Bayes estimator we've been deriving is just a point estimator. We also want to have an interval. And they give you data. They say if prior, of course, they're going to give you prior mean, prior variance, likelihood is for you to be able to get your posterior, right? Posterior mean and the posterior variance. Now, when you take a look at all of this, if prior to observing any data, we believe that there was a high probability that mu was between 2007 to 2009, we might choose to use a conjugate normal prior for mu with mean that and variance delta squared. That is going to be a prior. Okay. Now, choosing shows that equal to that and that equal to that, this blah blah blah. Know that we have assumed a considerably more knowledge of that. Then at the end of the day, you have this data. You have 8 data point. Okay, when you have 8 data point, they ask you to find 95% credible interval. Okay, now what you're going to do, your n equal to 8. What is the sum of the observation given? You get the sum of the observation given. You have been given sigma naught squared and this from the question. Okay, now if you take a look at the approach I'm using here, this was based on the approach that have to do the derivation that I say you should ignore. So this is another way. The first one here is posterior mean. If I want to get posterior mean, if I want to get the posterior variance, it's still the same thing. If you just follow, even if you follow that A and B stuff, it's still going to be the same. And at the end of the day, look at what we got. Whatever approach you use, this is your posterior mean. This is your posterior variance. But what do we want to do? We actually want to find 95% confidence. And that very 95% confidence is actually going to base on the mean. You remember what we always do, okay, based on the mean. Okay, now it's going to be that guy, the mean, minus y 1.96, 95% confidence. Okay, so data, what is our data here? That is the square root of the posterior variance. Then you add, you subtract. At the end of the day, I'm done. It's easy. I'm done. But I'm not breaking it out. Okay. Now I'm going to go to the next one. We also have Bayesian Test of Hypothesis. Okay. The same way we have hypothesis testing under frequencies, we also have a Bayesian set of, but we got a condition on that. Let's say, for instance, we want to test this. You know, the unknown parameter level is under the null hypothesis. We say it lies in that parameter space. That parameter space, you can see omega 0. That's a parameter space. Because why are we using parameter space? Because the parameter here is now fixed. It's a random variable. There are going to be so many values in the parameter space. Unlike in the frequencies that we normally say mu equal to 0.5, mu equal to 5, because those ones are fixed. Parameters are fixed under frequencies approach. But in the Bayesian setting, we normally say, okay, parameter lies in a parameter space, and the alternative, it lies in another parameter space. Does that make sense? Then we're going to have a condition of either rejecting or accepting. Now, I need you to take a look at this. These are the conditions. We accept H naught if the probability associated with that parameter space in the null hypothesis is greater than the probability of the parameter space in the alternative. You know, this is what I call parameter space, in case you don't know. Okay, this guy, we call them parameter space, because parameter is a random variable. This is not going to be fixed. It's going to be different from the one we used to do. Oh, mu equal to 50,000. No, because that one is fixed. We're using the frequencies. But right now, we're actually going to be using the parameter under investigation varies, a random variable. So we're going to say that. So the condition for accepting is this guy. Okay, we accept H naught if that happen, and we accept H alternative if that happen. Does that make sense? We base it on the probability, okay, of a parameter that lies in the parameter space under the null and the alternative. Okay, if you want to do that, in example 16.5, you know, the example that we did the other time, this guy here, under, you know, that we use for confidence interval, that we have data. Okay, let us now assume that this is our hypothesis that we want to test. Okay, 2,950 and greater than that. Oh my God. Under the frequencies approach, we normally use equality here. Why do we use less? Because there's so many of that. Does that make sense? And even greater than that, there's also so many of that. So let's say this is an hypothesized value. Okay, we're testing for. How are we going to proceed? We need a probability. You know, I told you, we need a probability of a theta under the non-hypothesis. What do we have under the non-hypothesis? The non-hypothesis is actually say less than or equal, right? Do you see that? We're going to find probability associated with that. We're also going to find probability associated with this. Take a look at this now. Okay, we want to find probability. Oh my God, finding probability associated with this guy will actually take me to z-score. What am I going to use? The mean is going to be the posterior mean. The standard deviation is going to be the posterior standard deviation. Do you guys love that? Or do you want this in your exam? It's super easy, okay? So now, the moment, so what I'm going to do now, I'm just going to check from the Z table. After solving from the Z table, what do I have? This is a probability now for this guy, for the non-hypothesis. Then I'm going to do the same to the alternative. If I want to do the same, don't forget the alternative is saying greater than. So for greater than, it's just going to be 1 minus the one in the table. Now, what do I have right now? Oh my God, I'm actually going to compare two probability, one here and one here. Okay, the first one is the non. I put the one for the non. The other one is the one for the alternative. And you take a look at this. We got a decision rule. Do you see the decision rule? We accept H naught if the probability in the non is greater. We accept HA if the probability in the alternative is greater. Now, which probability is greater now? Which probability is greater? Oh, is the one in the alternative. Is that not super cool? And that was why we see that the posterior probability of alternative is much larger than the posterior probability of H0, and our decision is to accept it, period. This is where I'm going to stop. Is there any question? On Monday, we're not meeting in this class.